Alright, this is Ken Rosever. We're going to talk about normal versus standard normal density curves. A normal curve is a bell curve, pretty much. It's significant because its mean, median, and mode. Its mean, median, and mode are all centrally located, and this distribution curve is predictable. And because it's predictable, we can use it. If we just know, a little bit of information, we're able to figure out areas. But a normal curve is not a standard normal curve. And before we can figure out areas and things like that, we have to standardize our information. So in the IQ example, the mean is 100. The standard deviation, I should use a notation for standard deviation. Let me do that. Is 15. So this would be 100 in the center. I'll put it down here. 100. One standard deviation to the right would be 115, 130, and 145, as we've seen on other videos. I think 85, 70, and 55. And this curve would be bell-shaped. That's our expectation because IQs are normally distributed. However, without standardizing our information, that is, without converting this curve into a distribution of z-scores, we can't actually use the cumulative z chart that's found at the end of, or table that's found at the end of your book or at the front of your book. We have to convert these data, and that's pretty much what this exercise in Alex is checking that you know how to do. Do you know how to convert a given value of x to a z-score? But not just that, do you know how to convert a given inequality related to a value of x to a inequality related to a value of z? First of all, you should know how to get a z-score. We've done that since chapter 3. If I wanted the z-score for, let's say, right here is, we'll say right here is, whoa, how'd that happen? 80. Okay? If I want the z-score for 80, I would go x minus mu over sigma, which is 80 minus 100 over our standard deviation, which is 15. So that would be negative 20 over 15, which we can approximate as negative 1.33. So that would be the z-score. So this 80 here would equate to a negative 1.33 here on the standard normal distribution. And if they shaded in, if they wanted to know what percent of people have an IQ that's higher than 80, well, we couldn't figure that out unless we figured out what percent of a standard normal distribution has a z value greater than negative 1.33. So to do anything with a normal distribution, you have to convert that normal distribution to a z-score. Now let's look at the problem. Going down here. So this is the problem they've given us in Alex. Below is a graph of a normal distribution with, and you can see it's normal. It has that bell-shaped curve. It's not as flat as you saw in my other things, but it's a little, not as high. It's a little more flattened out, but it's still bell-shaped. The mean of this bell curve, this normal distribution, is negative 3, and that is where we see the peak of the bell. And the standard deviation is 2. So that means this right here from negative 3 up to negative 2 is half a standard deviation because it's only gone up by 1. The shaded region represents the probability of obtaining a value from this distribution that is less than negative 2. Shade the corresponding region under the standard normal density curve below. So they want us to equate this negative 2 to z value and then shade to the left of it, which is very straightforward. We have everything we need. We have the mean, we have the standard deviation. We can certainly find the z-score for -2. And when you plug it in, you go -2 minus -3 divided by 2, and you get +1/2. You can check me on that. Here, I'll do it with a calculator. What was it? Let's put it in parentheses. -3. How do I do a negative on here? I guess I hit this. -3 minus negative. Oh, I can't. Oh, I gotta hit the plus minus key. That makes sense. Negative. Oh, nope, that doesn't do it. I don't know how to do negatives on this calculator. That's kind of weird. Okay. I won't bother doing it that way. I'll just do it right here. Alright, here's what we have. And marking this off, this is -2. That is the x-score we're interested in. Mu is -3. So if we find the z-score, it's going to be x minus mu over sigma. So it is -2 minus -3 over sigma, which is 2. When you have a double negative, that becomes a plus, and 3 minus 2, or -2 plus 3, is 1 over 2, which is 1/2. So our answer for z is 0.5, our z-score. And going back to this, and Alex, all we have to do now is put the line at 0.5. Did I say 0.4? I'm mistaken. And then shade to the left of that line. And that's it. It's very, very straightforward and easy. Okay? They said very good. So basically, when you standardize this, you get that. Let's do another one. This is also a normal distribution. You can see from the graph the mean is at 2. The value of interest, x, is at 4. But before we can do anything, we need to know what the standard deviation is. And you can see here the standard deviation is 4. So we would be doing 4x minus mu, 4 minus 2, which is 2, divided by 4. And once again, our answer would be 1/2. That's kind of crazy, but it happens. And we just apply that, shade the... Did I shade the right side? No, I did not. I think up here I had the right side shaded, so I need to shade the right side. Okay. Do one more? Sure, why not? I'll practice again. And this will be our last one, and they'll add it to my pie. Ah, a little more involved, because they want the region between 5 and 6. So what does that mean? I'm going to have to convert 5 and 6 both into z-scores. Well, that's not hard, because I can see my standard deviation is 2. So 5 is a z-score of 1, 6 is a z-score of 1.5. And you can confirm that just by looking at it and imagining that since sigma is 2, one standard deviation away from 3, the mean, is 5, and 1.5 is 6. So that's, or you can use the formula to confirm that. But it's 1 and 1.5. So over here, I put that at 1, I put that at 1.5, and my area of interest is between those two. And that is it. Very straightforward. We're done. It's added to our pie. I hope this was helpful.